As I said, I'm George Allman, for those that don't know me. I'm the manager here at Pukaki Downs. And our interest in biochar started some years ago. And I'll give you a little bit of the history of how we became interested. As most of you know, we've got a huge wilding pine forest, which has been existing for over 20 years. And we started realizing that we were so frustrated in terms of dealing with the regen and the spread from the forest. For years, what we did was had scrub bug gangs come in and clear all of the clear areas of the property. And that actually was a bit of a thankless task, because every 3 years we had to rotate and do that exercise all over again. So what we realized early on was we had to get rid of the seed source, which is the forest itself. Because if you don't get rid of the seed source, you've got this ongoing battle with regen on the property and potentially spreading to neighbours. So what we did was we actually entered our forest in the ETS, which was unpopular at the time because wilding forest people were not very happy about that, but we managed to get it in. The idea of doing that was we realised we had to fund the clearing, and at that stage there was no government funding available to clear wilding forests, wilding pines. So we entered in the ETS and sold some carbon credits early on and used that to fund root raking the big trees and then windrowing and burning. But one of the things we realised early was that burning big windrows creates a huge amount of smoke. And I can remember some of the early windrow burns we did. The smoke literally travelled all the way to Twizel and covered Twizel. And I'm thinking, we didn't get too many complaints. People were tolerant of this, but at the same time we realised ongoing for 1,200 hectares, that's not a feasible option moving forward. So then I started looking at other ways to deal with the forest. And for a few years we were talking with a UK company, a large UK company, who were quite serious about turning the whole forest into pellets and exporting the pellets to Japan. And they were going to set up a pellet plant on the property to do that. That didn't end up working out. And then we got talking to local companies, and then we made a deal with Pioneer Energy to take the whole forest for biofuel, harvest and chip the whole forest. And now they're in the process of doing that. They're a year into that. And what they do is they harvest the wildings, chip them, transport them in big trucks down to their Timaru base at Washtag. So that's going to take a process of quite a few years to clear the whole forest, but that's what we're doing right now. But anyway, back to the interest in biochar. One of the first things I learned about it was that you can burn a big pile without creating so much smoke. And hopefully today we'll be demonstrating that. And that's one of the attractive features. And also at the end of that, you end up with a product which is actually a useful product. And Phil will be talking more about the potential uses for biochar. So anyway, we've been talking to Trevor Richards. Here's Trevor Richards. He's the secretary of the Biochar Network of New Zealand. And been talking to him for several years about...
10 years ago I first...
Well, 10 years, Trevor?
The truffle conference.
Well, that's when I first met you. That's when I first met you. But about biochar for the last few years anyway. So we're very grateful that finally we've managed to organise this day with help from Trevor, Phil Stevens, and some of the other guys that are managing the burn. They've started the burn already. It's good to see you guys all here. Some have travelled a long way. Trevor's come all the way from Malaysia, so that's pretty. That's others from Christchurch, and so appreciate the efforts you've made to come and be here.
Kia ora koutou. I'm Phil Stevens. I'm the deputy chair of the Biochar Network New Zealand. Huge thanks to George for being a gracious host, kicking this thing off, pulling the strings, and gathering us all together today. This has been, as these two guys have conversed over the years, quite some time in the making to get sort of the local center of interest here around two things that overlap quite well, and that's the environmental management of the wilding pine problem and the all the benefits that we can get out of biochar as a yield from responsible ways of controlling the pest plants. So we're here today to hopefully keep the talky bit short, but I'm going to do a bit of show and tell and some of the sort of the highlights and overview of what biochar is, how it's made, why we do it, some of those things. And then when that's all said and done and we've had a bite to eat and a hot cuppa, we're going to amble down to the clearing there where they've got a couple burns going live, some biochar they made yesterday, and get to see the process up close and personal. And so I'm sure there will be lots of questions, lots of discussion, lots of interesting ideas today, and just looking forward to what transpires. So we start with the basics, the FAQs of biochar, and for the definition, as we describe it, this is a paraphrase of the International Biochar Initiative definition. It is a form of charcoal produced at sufficiently high temperatures to drive off all the volatile products of combustion and leaves behind a porous structure that is mostly pure carbon with some minerals, and obviously those are the minerals the plants took up while they were growing, and it is usually intended for use in the soil. So it's not something that's going to be used as fuel, heat, energy, but there are other uses of biochar that aren't necessarily soil incorporation. It's got a lot of value as an aggregate in paving or metal replacement. It can go into concrete, plasters, so a lot of building materials. And there's even a lot of interesting technology applications because of the form of molecular carbon that is produced. It is a precursor to graphene. And so it actually has use in things like supercapacitors and a lot of other interesting electronic applications. So it's a very useful product. And the big headline for us, though, and the reason why a lot of us got interested in biochar in the first instance, is because that carbon that comprises most of biochar is a very stable form of molecular carbon. It does not degrade, it does not weather, it does not react, and it is not really broken down on exposure to the elements or microbial activity. So once you've produced biochar, that carbon is effectively locked up. A small percentage of it will, over time, will weather and mineralize, but most of it is a really durable, safe means of sequestering carbon for the long term. And we make it usually from woody biomass. That's the most typical feedstock. So in this case, we've got an awful lot of wilding pine around the place. It is a pretty obvious thing to use. It's easy to produce from woody feedstocks. There's a lot of biochar made from things like bamboo, crop residues like corn stover. You can take dried manure solids, makes quite a nice biochar. And then waste streams from food processing are another common use. The main thing that we say with biochar is we just keep problematic materials out of it. So no tantalized timber, no paint, especially old paint that could be lead-based. So we just keep out anything that could leave behind a toxic or hazardous residue. But other than that, pretty much anything that was living is fair game. Then the things it can do, I've already talked about the carbon sequestration. That can extend well into the thousands of years, and there are lots of examples of biochar or pyrogenic carbon that has been recovered from soils and sites where it's been very accurately dated at In the Amazon, 2,500 to 3,000 years. And in places like the temperate prairies of Central North America and the Ukraine, they have these deep black prairie soils. Those contain a significant fraction of fire-derived carbon. That in the Midwestern United States, that's 7,000 to 8,000 years old at least. In Ukraine, it's 14,000 years old. So this is biogenic carbon that has been there, and because of the conversion by fire, it has stayed there effectively unchanged for millennia. So safe way for us to sequester carbon from growing plants and lock it up, put it somewhere where it's beneficial, and solve a pretty pressing problem. The thing about the feedstocks we're using, if these windrows are lit off, then all that carbon is basically going, or nearly all of it's going back to the atmosphere. If it's left to decay slowly in the environment, it will wind up back in the atmosphere. It'll take a little longer, but it's all destined to go back into the system. Biochar is a sort of a parking solution where we take about half of that carbon and put it somewhere that's not going to go back to the atmosphere. The things that it does while storing carbon are what get people excited, though. So when you put it into soil, it doesn't just sit there. It helps with moisture retention. Trevor, if you take these two bags and just hand them around. So this is our very simple example. These are 2 equal volumes of biochar. One's bone dry and one is saturated with water. It holds roughly 3 to 4 times its weight in water. It also helps aerate. It provides a medium for gas exchange. So in tight soils, it's a good way to open up the structure. The molecular surfaces of the biochar, of the carbon, have attachment points, electrochemical attachment points, that can grab onto ions, like nitrate ions in solution, hold on to them, and keep them from leaching into the groundwater. So it's got a lot of benefit in pastoral and arable applications for that. And then one of the really exciting things that it does is this porous structure that's left behind when you burn off all the other bits in the timber has an incredible amount of surface area. The biochar you're passing around has been tested, and it's got about 300 square meters per gram of material of effective surface area. So if you took a handful of that stuff, that would be roughly a hectare of surface area in all those little nooks and crannies. That's like a coral reef for the soil bacteria and fungi. They love it. They move in there, they set up shop, and they basically find a refuge from the things like the grazing nematodes that are always out hunting them. So it's a really good place for them to get a bit of a habitat and repopulate and replenish the soil biota. So it's that's one of the big things biochar does when it goes into productive soils, is it leads to an increase in overall biological activity in the soil, and that of course lends itself to fertility and more carbon sequestration happening organically in the soil. So we call these the cascading benefits of biochar. It can be used as a water filtration source. So just like activated carbon, you can let water slowly move through it, and that ionic attachment will pick up impurities and hold on to them. It's getting a lot of purchase in the livestock and animal health side of things as a feed supplement, and I already touched on what it can do as a building material. So a whole bunch of things you can do with biochar, and the research and the new applications are just coming thick and fast. All sorts of things that people are doing with this stuff. And the other question that often comes up is people ask, is it new? And the answer is no. It's been around as long as there's been fire on this planet, and that's been 300 to 400 million years. So as soon as terrestrial vegetation showed up and started to dry out, it would catch on fire now and again. What has happened over the millennia is fire cycles have developed in nature in concert with the evolution of various ecosystems. So you have all around the world places where vegetation grows up, becomes crowded or tangled or senescent, dies, and catches fire. And that's all part of this cycle. And then, of course, we came along and very quickly figured out fire, and since then have co-evolved with it. So fire is sort of an innate part of our being and the way we roll. And it's responsible for a lot of our own our social and cultural structures. It's why we have smaller jaw muscles, because we cook our food. So that gave us a little bit more space for brain development, which was another step change in human development. The thing that people have done, of course, is taken fire with them into places where maybe it hadn't been, or they have changed a fire cycle from one type of time basis to maybe they shifted seasons, shifted the frequency. But all this is to say that anytime you have a fire in nature, it doesn't burn everything to ash. There's always going to be some charcoal left behind. And on a global basis, landscape fire converts about 1/8 of the carbon that it consumes into a biochar pyrogenic carbon form. So fire is not necessarily a bad thing. We need to manage it. We need to work with it. We need to accept its place in some landscapes. Unfortunately, most of New Zealand's ecosystems are not fire adapted. In fact, a lot of them are very fire averse. And what we have done since colonization is provide a lot of fuel for a lot of very unnatural fire regimes. So that management, that re-shifting of the fire cycle is something we need to do, and biochar's production is one way we can do that, and we can use that to responsibly manage some of these landscapes and hopefully prevent and ameliorate the damage that can be caused by wildfire, as you would have seen driving in. So to make biochar, we're doing something called pyrolysis. Pyrolysis is just a simple technical term for heating material in a reduced oxygen environment. And most woody feedstocks, most biomass type feedstocks that we're using, as long as they're dry, have more than enough caloric energy embodied in them to power the entire process with heat left over, sometimes 2 to 3 times as much heat as required. So you've got what's called an exothermic process in chemical parlance. And then we've got quite a few different methods of producing biochar, a lot of ways to do pyrolysis. And these are just something we try to match to the available resources, the capital and operational considerations, what sort of labor requirements they have, what the form factor is of the feedstock. Is it whole trees? Is it logs and stumps and root balls? Is it slash prunings and thinnings? Is it chip? Is it is it fine? Is it big and chunky? Is it a mix? So once we know these things, we have a better idea of what sort of process we can put to the task. And then out there in the real world, there are all the way up to quite large industrial units. This is produced by a German corporation. Quite a few of these installed around Europe. A lot of companies and municipalities are using these to deal with forestry residue, municipal solid waste, things like that. So this is quite a big unit, and it's designed to run continuously, and the output is measured in tons per day. So it's quite a bit of stuff being produced, quite a bit of material going in, and a lot of heat coming out. These will typically have cogeneration, so they'll be producing electricity, feeding that back into a local or large-scale grid. At the medium scale, we've got some of these units. These come out of Australia. The containerized unit is what's called a batch system. It's loaded up with stuff. Those could be broken down pallets. They could be logs. They could be full of wood chip, offcuts, whatever. I think they've done quite a bit with things like sugarcane, post-processing sugarcane residue. It all gets loaded into this container, which is lined with refractory, closed up.
How's it loaded, Phil? It seems
There's
closed top.
forklift. So forklift loads these smaller containers into the big shipping container.
Baskets.
So
they put 'em in.
they're like big boxes, and they just go in, come out. So those are all loaded in, and then heat sources applied, and then once it's the off-gassing starts, and the process drives itself. This other unit is a continuous system they've devised, which processes wood chip, and that'll do maybe a few cubes a day, and that could also be used for poultry litter. This is what we call a T-LUD, top lit updraft, and the unit on the left is basically it's a large steel vessel, and inside it are drums. So there may be 2 or 3 55-gallon drums in there, and they will have a lid that is set on the unit but not clamped down, or maybe some holes poked in it for the gases. The evolved gases need to escape, otherwise you've got a bomb. And then the exterior perimeter of the unit is packed with sacrificial feedstock, so you may be putting split timber kindling in there. Inside the barrels you've got your biochar feedstock. You light the whole thing from the top, and as the material burns, the flame front moves down, and the combustion gases travel up through the flame, so it's quite a clean burn. The heat penetrates the inner vessels and starts to pyrolyze the material in there. They then begin to release the combustion gases. That feeds the process, and the fire gets about 5 to 10 times as intense, and it really goes. That's another batch system, basically. You light it, you wait for it to finish. These ones on the right are a really cool adaptation of that technology. It's a cook stove. So it's got an inner vessel, and then the outer one is packed with shavings or wood chips, lit from the top. And one of these will burn for about 20 minutes. So that may be long enough to cook a pot of rice or a spaghetti dinner. If you've got something that needs to go a bit longer, you've got another one waiting. So when the first one finishes, you can light the second one and just slide it under. So this is actually a very practical way, not just to make a bit of biochar, but also it's a very efficient and clean burn. It's a very good approach to improving cooking for people in third world countries, so they can use less fuel. They won't have to travel as far for fuel wood, and have much cleaner air, because the traditional charcoal cooking fires that you find in places like Asia and Africa are very smoky, and the respiratory diseases, the rates of people getting sick and chronically impaired from the air pollution from their cooking fires is horrendous. So this is just another practical way, and it just happens to make biochar as well. So, it's a win-win. You've got an efficient cook stove, uses a lot less fuel, and improves the air quality. So it's just another way that we've got all these cascading benefits from the technology. And this is my log burner, and in it you can see a couple of these stainless steel roasting pans. With the lid that just sets right on them. Load these up with offcuts, wood chips, nut shells, whatever, and I put them in. And the photo is taken as the off-gassing sort of reached its peak, so you can see the flames just roaring out, and it actually lifts the lids a little bit from the pressure. But then as the fire dies down and the off-gassing stops, that lid settles right back down, and it excludes any further air or oxygen from reaching the coals inside. So they just go out, and it leaves behind a beautiful, very very pure form of biochar. And I get to capture the heat and heat my house with it. So it's a very simple way to just make biochar throughout the heating season. What we're going to see today, though, is not a retort system. It is what we call flame cap pyrolysis. And the basic gist of flame pyrolysis is we're always fueling the fire. We're just feeding a fire and maintaining a cap of flames across the top. And this is the game changer in open burning because it means we're eating all the smoke. We're using the flame to control the smoke, control the heat, and limit the oxygen. So the sides and the bottom of our vessel are containing the heat, containing the fuel, and they're concentrating it and they're controlling the airflow. And that's the really important part because we've got this active flame across the surface. And that flame is consuming everything that's coming out of the wood as it burns, consuming the particulate matters, consuming all the gases. So it's good, hot, clean burn. But the other thing that flame is doing is in doing that, it's using up all the available oxygen. So the bed of coals beneath the flame cap is safe. It's protected from any further combustion, and so it doesn't burn all the way down to ash. So it's limiting the airflow, keeping the coals preserved, and giving us a nice clean, ideally you want to be able to look through that flame cap and see nothing but the shimmer of heat, no visible smoke, no pollutants. And then when the burn is done, you just quench it with water or put a lid on it, or if it's in a pit, you can just push dirt over the top to exclude the air, and that puts it out, and congratulations, you've just made biochar. So there's some very simple and common variants on the flame cap. The left one is a small Kontiki. That's sort of like a little residential lifestyle block size one that I make. It's 300 liters, and you can cart it around like a wheelbarrow, tip it out. It's got an inlet at the bottom to flood it, and that's really nice because you don't have the problem of steam and explosive behavior from putting out a hot fire. The one on the right is called the Oregon trough kiln, and there are variants of this. This is based on a thing called the Warm Heart that was developed in Thailand. It's quite a big rectangular kiln with sloping sides, and those sloping sides are a feature you'll see. They help to create the flow patterns in the flame cap that we're after. It's called a rolling vortex. So those are about 1 to 2 cubic meters each, and what they're doing in the western United States is taking these out to forestry sites and using them to process a lot of slash and debris. Then you can go a little bigger, and these are some ideas. People got to take big fuel tanks or water tanks, cut them in half, and use those for vessels. The neat thing about these cylindrical ones is when the burn's done, you can just take a large excavator and flip it over to extinguish your fire. You don't need water. So that's the turtle flip. Quite a neat little innovation there. And once again, you're keeping things contained, which is really quite important if you're out in a setting where you've got dry grass, litter, and things like that, or even soil that could be combustible on its own, peat soil. And another innovation that's come out of the western United States recently is the Ring of Fire. This was developed by Kelpie Wilson, who does a lot of that forest management burning. And she came up with a really neat design. This is open source. She publishes it on the internet. It's just sheets of plate steel with angle fittings put together by bolts. They can be taken down, flat packed, put on a trailer or the back of a ute. I think she said these even fit into a Subaru station wagon. So you just take it to the site, assemble it. It's just a cylinder, and then it has a rim around it, which is very good because it means you can walk right up to it without getting roasted. And then when you're done, you just take off one of the panels and you can scoop the char right out. So it's a brilliant design, and she's got many of these out in service around places like Oregon, Washington, California. And you can go even lower tech. So these are examples. On the left, we have an example of a pit, and Shane just dug a conical pit and then he's got this little rim that just sits at the top of it. So it's like a Kontiki in the ground. And it works the same way, except you don't have all that steel to carry around. You can also dig a trench. We've got a pit down at the site we'll be showing off. And then the lowest tech of all is a pile that is simply lit from the top. And if there's one takeaway from today, it's the way we light our fires. And I'll talk a bit more about that, but this is a pile of eucalypt slash that we did. We did a couple of these on the day, and we got probably about 3 or 4 cubes of biochar out of the whole burn. The yield is not as great because you are burning more of it to ash, so about 10% from a pile, whereas most of the flame cap vessels would give you 25 or even 30%. So yeah, I say the game changer, lighting from the top is the cool thing, because as the fire burns, the flame front travels down, it heats the wood and starts it burning, but all the combustion products want to travel up. They travel up through the flames, and all, or hopefully all, most of them get consumed by the flames. So far cleaner burn, far less smoke. A little bit of smoke is usually unavoidable, but if you compare a pile like this was about a 6 by 6 meter, 4 meter tall pile of fairly fresh pine. It was only been cut about 4 months earlier. You can see a little bit of black smoke in there, but we didn't get any of the white smoke that you would ordinarily associate with a pile like that. So really quite a clean, very, very hot burn, very quick. So when we're doing a flame cap burn, it's an interactive process, so it's hands-on, and the rate of adding fuel is what it's all about. It's the size, the amount, and how much you add at any given time. We want the flames across the top, and we want no smoke if possible, but every now and then we're going to get a puff. The color of that smoke tells us what we need to know. If you see white smoke doing a flame cap burn, that means it's you've cooled the combustion zone. You've cooled it to the point where those volatile products are not being fully burnt, and they're escaping into the atmosphere. So those are the tars and the oils, and unfortunately, there's methane involved in that white smoke as well. So we really want to keep that out of the picture as much as possible. Black smoke, on the other hand, means you've got so much fuel in there, and it's so hot that the fire is just a little bit too happy, and it's overrunning the amount of oxygen in the flame cap. So you're getting some condensed carbon, which is soot, in the flame stream. We'd also rather not have that, but that's a little bit less bad than white smoke, because the black smoke doesn't travel as far. The white smoke is the stuff that will go down to Twizel and stick on people's laundry. So with any of these situations, if you see smoke coming from your flame cap burn, it's basically fixed by backing off. You just wait and it will fix itself. But if you've got white smoke and you've got some fine dry fuels on hand, you can fix the condition by sprinkling a few pine needles, some cabbage tree leaves, some dry paper. Any of those things to get the flame cap going quickly should take care of the white smoke. With black smoke, you just have to back off and let it settle down a bit. The other, the flip side of that is too little flame, and what that will do is that will expose the biochar to air, and it will start burning to ash. So if you see ash forming, that's just a sign that you need to add more fuel and get the flame cap reestablished. Or if you're out of fuel, it says it's time to quench. So once you've made your biochar, what do you do with it? And that's the $64 question. And we're sure that a lot of the people in this room already have the gears turning or have played around a bit with possible things they could be doing with biochar. But the really obvious ones are to just get it back into the ground, close to where you made it, so you don't have to truck it somewhere. So that obviously means incorporation into pastoral and arable soils, into forestry. So if you're making it in a forestry setting, it can go right back where you made it, and it improves the soil, improves the regeneration if you want forest there. As a side to forestry establishment, there may be a nursery and propagation effort. Getting biochar into the potting mix is a great way to enhance the early growth of seedlings. And when you're planting out tree seedlings, a little bit of biochar in the planting hole really helps their resilience and establishment, because you get that moisture retention, and you just give them a much better chance at survival, especially if you've got a dry summer situation. Horticulture and viticulture is an obvious one. The animal feed sector is one we're quite keen on, because we've heard some great stories from some farmers that have fed biochar, recorded really impressive weight gains and health benefits. Obviously, home gardeners and lifestylers are a large potential market for this stuff. Water quality remediation is something, I think every council ought to be aware of what it could do if you've got things like drains or constructed wetlands. You could put sacks of biochar in them to just let the water filter through them slowly, haul the biochar out periodically and replace it with fresh, and then use the stuff that was in there on the land somewhere. And then, of course, the other huge driver for biochar in an economic sense is, although it's not recognized under our ETS, and there's no official designation of biochar as a carbon capture methodology, there are voluntary markets, there are international markets where you can trade credits in quantities of biochar, and these are picking up and becoming quite lucrative for some producers. I've seen recently in Europe where some biochar producers have been getting €500 per ton of CO2e in credits. Over in Australia, it's not quite so impressive, but it's still decent money. It's about $150 a ton. So it becomes quite an incentive to produce this stuff, and if done right, it could pretty much fund the operating expenses of a stationary plant. So these carbon credits are, and this is just the beginning. As the price of carbon goes up, those markets will become even more of a factor. So that's something we're really hoping we can, excuse the pun, light a fire under in this country. And at this point, I leave us with a nice microscope photograph of a sample of biochar showing that beautiful pore structure. And I open up to Q&A if people have any burning questions.
One question about that: if we could spend an hour or two on Q&A, and should we try and get the Q&A, most of the Q&A, after we get back from the fire, or around the fire, or when we get back from the fire?
Yeah, I reckon if there were any really hot topics, we could cover them here, but for the most part, I expect a lot of stuff will be talked about down on site, but sometimes there are some very general questions that it's good to get with everybody in the room. So if anybody's got sort of a general...
And there'll be time for that later as well.
Yeah, and we'll be
lunch.
coming back to it as well after lunch.
Is there any industrial size production at the moment?
In New Zealand, we have one large-scale producer, and it's an accidental producer. It's the Red Stag Timber Mill in Rotorua, and it's simply because of a quirk of the way two of their process heat boilers are set up. They're just basically, all the mill waste, all the sawdust and offcuts.
They're very old boilers, and they've been producing it for years and sending it to a certified landfill for 20 or 30 years to get rid of it. They were just blinkered on process conditions for driving heat, and they had a lot of fuel left over, so they get variable stuff coming in. It doesn't burn properly. They didn't care so much. They had plenty of fuel. So they were creating a accidental biochar, which is a reasonable quality, 50% generally, 40% carbon.
Which country around the world would be leading it in terms of industrial production?
Well, in terms of quantity, North America is punching above its weight.
China's the biggest.
China's
China's the
huge.
biggest in the world.
China's huge.
They've hit it hard.
And Europe. There's an awful lot going in Europe. Australia is also starting to really gear up. Yeah, we are lagging. It's embarrassing with all the biomass around this country. We should be leaders in this space. We're a good 10 years behind most of the other countries that are doing biochar. Yeah.
There's a bit of agricultural politics behind where we've ended up, because we did have a good lead at one point. I would say when we set off there was a research centre set up in Massey, and we were probably part of the world leaders at that point of government investment in biochar, and it all just lost its way.
How long ago was that?
When did that start?
About
2005?
12, 15 years ago. 2008, I think, is when the centre was
Yeah, they
funded.
funded it about 2005 maybe. So they couple of professors down there, one on soil, one on chemistry, and they've generated 8 or 10 PhD students went through that over the years till the funding stopped.
Right. And nobody else is doing research at the moment?
Yeah.
There's research going on around the place. There's some going on at Canterbury, at Lincoln, Waikato,
Auckland's doing a
Auckland.
lot.
Yep, it's happening, but there's no connected. There's no linkage between the centers, and the biochar center at Massey is dormant. So, yeah.
Sorry, I recently had a presentation very similar to this, a company called Carbon Lab, but they seem to suggest that the end product was super refined. Do you know anything about that?
That sounds like marketing to me.
It was definitely a marketing pitch, but
Yeah.
is there a next stage on from your...
You can. There's a lot of work going on that.
Yeah. So effectively, biochar is just a step along a continuum to technical activated carbon, and to get to that step, you go through some extra industrial processes, usually involving acid to remove the mineral quantity, and steam to open up, to expand the pores. Now, one of the neat things about flame cap pyrolysis is that when we quench one of these burns with water, especially if we flood it from the bottom, there's a lot of superheated steam going on, and that actually does do some of that pore expansion. And when I had my biochar tested and it came back with that 300 square meters per gram figure, the people who tested it are the activated carbon plant up in Taupo, and they said, that's a really good number. Whatever you're doing, keep doing it, because that's a high surface area. So there are things we can do, but really, if you start with good feedstock, that doesn't have a lot of contaminants in it, just about any biochar made from wood or timber byproducts is going to be at least 80% pure carbon. That remainder is going to be the minerals that were in the wood. So it's going to be calcium, magnesium, sodium, all the non-burnable components that were there. And those are plant nutrients. So it's not a bad thing from a biological perspective to have that mineral stuff in there. Softwoods are going to be higher carbon, so pine is going to be up around 90. Hardwoods will tend to be 80 to 85.
It's just the ash, really.
Yeah.
Is what's carried with it.
Those big units, how much do you have to feed into them a day?
If they're producing tons per day, then it's 4x tons going in, because that's the mass and volume reduction is about 4 times.
And those examples that Phil's given are really just scratching the surface. There must be biochar companies, commercial biochar companies, there must be at least 20 or 30 around the world that have got commercial products available now, and probably double that or more that are developing in various stages of development of industrial commercial scales, at all different scales, all different methodologies. So it's a really broad subject right now at an industrial level. I mean, there's some great opportunities in New Zealand around this as well, on existing plant. Companies like BlueScope, Glenbrook have 4 massive Herreshoff kilns that basically are char makers that process coal and steel, and of course they're potentially going to become idle with the new investment at BlueScope. So. Yeah, and all of these biomass boilers that are being changed out in New Zealand, they're all, in some ways, they're missed opportunities probably where pyrolysis could be introduced where there was available feedstock. but at the moment there's not a lot of thinking going on. There's just a rush to biomass boilers where they can do it.
Yeah, in a way, you don't want to let the perfect be the enemy of the good. You know, we're happy to see the biomass conversions take place, but like Trevor said, it's a missed opportunity. We've got so much feedstock that if you're willing to accept a higher throughput of material, you get this extra output, which is sequestered carbon with all these other cascading benefits. So yeah, it's something we'd like to be promoting as much as possible.
How technical, how easy is it to top burn?
It's super easy. Yeah, it's like standing around a fire. Yeah, it's really if you've got a small Contiki or pit or like a barbecue. I should have put up a picture of Dennis's barbecue, a cast iron bath.
Baths are used a
I'm
lot.
thinking of windrows.
Big.
Oh, okay, now windrows are problematic, and yeah, I'm glad you asked that, because you could top light a windrow or top light one end of a windrow and get it going, but I think it would get out of control on you. My experience with piles is a big pile is about as far as I would want to go in an open burn context. If you top lit a windrow, it would race down that thing, and most of it would be ash, heat and ash. You would start with a clean burn, but as it traveled the length of the windrow, I think it would go more into a standard slash burn, and you'd probably get more smoke.
So are you saying you'd be better to break up the windows?
Well, the pit is the answer, I think.
Yeah, I think Trevor's right. The pit, because controlling the airflow on the sides is the key.
So we've been thinking about the pit thing for a long time, and we've got some designs that haven't been fully tested. We want to get them tested, but there are people, there's a crowd around Wellington that have started doing some testing and got some funding on pits. We've got a pit demonstration going on down there, and I've done some work on thinking about how to do a large-scale windrow into pits, so it's like a continuous operation all day, and you're making a seam of biochar backfilled, and that can be recovered later. To me, it's still conceptual, but we're hoping to get support to test that model, and we could bring up some examples. Maybe this afternoon we could pop that up. Trevor's got put quite a bit of thinking into how we would do this, so maybe we'd have a little bit more detailed discussion of it later.
So in lieu of a pit, a conical pile would be a better windrow.
Yes.
Not necessarily a conical pile. It could be like we call it a rec build, or building a nice clean pile. You'll get a better result with uniform size material, interlaced, giving some airflow underneath. So just a pile of roots and root balls and everything pushed together with a bulldozer is not going to create a good result. You need probably a large excavator in there and do a bit of sorting out.
If you build a bit of a Jenga tower, it really goes.
So what about the option, say those windrows we passed coming up the road there, which we all look at and want to get rid of with least smoke and maybe biochar output, pushing up dirt on either sides to control that basal airflow?
Yeah, I think the problem is that as the fire travels and races down the windrow, it would probably get ahead of your ability to, unless you pre-piled everything, and that would be an awful lot of dirt moved all at once.
Easier to dig a pit beside the windrow.
And just push in a bit at a time.
And burn and light the whole top at one time. Don't you give it a chance to race down, it's burning along the top the whole way.
Yeah, I suppose if you had the right conditions, it's worth testing. I mean, I think there's a lot of concepts we haven't tested at a large scale, and I think
Site
we
down
want.
there.
I think the problem you'd have in Mackenzie is nobody from Mackenzie District Council is digging pits.
So we've done this is what we want to show you, the economics. I've tried to delve into the economics of it as well, and the productivity and what equipment you need and so forth. So hopefully that would try and you've got to be able to sell it as an economic, a viable production system.
Probably for the council, more of a biodiversity argument rather than economics, because the issues around resource consent is around soil disturbance and
sure. So we want to test this though, so we just need to gather support to try something out.
What's the biggest bulge of that?
that pile I showed back around the center of the presentation, so that was about 6 by 6 and 4 meters tall, and it had some pretty big logs in it. And it got exciting because as it settled, it was fully aflame, and it was a thing to behold. As it settled, one of those logs levered up and became a trebuchet and lofted burning fragments all over a hillside. And so we all changed into volunteer firefighters for the next hour and beat out about 24 spot fires. Fortunately, we had everything on hand. We had wet gunny sacks and shovels and lots of water and a pump, and there was no incident, but it was exciting.
There's been some big pile burns in vineyards in California.
Yeah.
Yeah, so there's some great photos online of some really big pile burns in California. Up in the Waikato, we did a big pit burn with a maize cob, 20 cubic meters of maize cob. I think we processed fairly quickly in a rather hot environment, and that was in a pit though. So there's all sorts of
For
stuff
me,
in there.
the most important thing if you're going to do a big stack is that if you've got consistency of the size of the biomass, then it makes it
Yeah, so much better. Yeah,
more
yeah.
better.
Yeah.
And if you've still got some big logs in there, well, they should have been pulled out and turned into firewood at a minimum. If there's big trunks, well, then they need to be sorted out first. They could go into a tub grinder and be made smaller or something like that. If you've got consistency of the size, it'll burn down really nice, really clean. It doesn't then move around so much, because the more it moves around, the more the air can get in, and then you're going to lose some
So-
of your yield
And
in
you're
the end.
doubling the amount of work to produce
Mm.
Yeah, and then you've
That's
got
the
to push it
downside.
back together and stuff. So
Yeah.
that's why the vineyard burns will be perfect, because all of the stuff's more or less the same size. You just stack it up in a nice shape.
So what,
Burn
if
down.
we look at it this afternoon, the pit one, I've got some ideas around how to handle that with larger logs, because it's about residence time with the timber. So depending on what's the rate of burn, I think it's like one hour per inch. I think is one of the things through a log. It varies, depends on how dry it is. But a big log obviously is going to take many hours to burn through. So you've got to keep that in the flame at heat for a long time. So it's about having all day to process some larger material. You need to be able to lift them, or if you get leftover brands, then you've just got to have a process of moving them into tomorrow's fire if it's a continuous process. So certainly I think there's ideas to test around how to solve these problems.
Is biochar a fancy word for charcoal?
Well, going back to that original definition, it is charcoal.
Yep.
It is about producing at a high enough temperature. When you make charcoal for fuel, you're often doing it at quite a low temperature because you want to keep a lot of those volatile products in it. It makes it easier to light. And we don't want that stuff in biochar because it clogs up the pores and makes it kind of useless. So it's about the temperature, the production methods, and the intent. The intent is not to burn it after it's produced.
The branding is quite important because if you get people who make charcoal just saying, "Oh, we do this here, we can sell this. This is worth more now as biochar than as fuel," they'll go ahead and do it, and they'll be selling you something that will take years to destroy your garden or your soil, because you're putting a whole lot of volatiles into your soil, and you've got completely different biology in your soil then to try and deal with those volatiles. So
the
it
answer
can damage
is
your soil.
it's not the same.
Not the same, really. We don't want that branding.
The other thing too is the methods to make fuel charcoal, unless they're done right, are really quite dirty. If you think of the old biochar kilns, or not biochar, the old charcoal mounds and things like that,
Earth
where
mounds.
they'd get a fire going and then they'd nearly smother it with earth, and it would sit there and smoke for days or weeks. That's awful. You don't want to be.
And that's
Your
what's still
downwind
going-
neighbors aren't going to like that.
So it's still going on in Africa, and some traditional kiln charcoal makers are still doing this method. It's horribly polluting.
Yeah.
So it's not. We need to change, really.
What are the risks of, producing all of this biochar and then putting it on the land with the condensed minerals, things like that? Are there risks to over mineralizing or adding in heavy metals that accumulate that then end up in the food supply?
if you're making the biochar from a clean, uncontaminated feedstock, then there's no risk. In terms of the quantity, you'd be hard pressed to make enough biochar to really alter the fundamental soil chemistry or makeup. You know, we're lucky in the settings that we're doing now, we're lucky if we can get 0.5% of the soil, the topsoil volume, amended with biochar. You know, so it would be very, it's kind of hard to imagine getting enough feedstock in one place and making enough biochar to make a real appreciable difference in the soil composition.
The other thing about that aspect is that biochar is being used for soil remediation. So this is why there's been such a huge push in China. In northern China, all the coal-fired power stations, there's a lot of polluting coal, cadmium contamination over vast areas of land. So they've seen that by making biochar out of crop residues and bamboo, they can remediate, they can capture that cadmium, and it holds onto the cadmium and makes it non-plant available. So it's actually providing a service to deal with some of these dangerous metals.